This video will discuss how to interpret inferences in multiple regression, particularly the F-test and T-test. The F-test is a global test used to evaluate the significance of the entire model, as well as the significance of individual independent variables. This test is based on the F distribution, a continuous probability distribution that frequently arises in statistics. The F-test for the entire model assesses whether the set of independent variables, when considered together, explains a significant amount of variance in the dependent variable. Specifically, it investigates whether all independent variables have regression coefficients that significantly differ from zero. The null hypothesis suggests that the regression coefficients are all zero and do not contribute to estimating the dependent variable. The F-test statistic is calculated by dividing the mean squared regression, MSR, by the mean square error, MSE. To calculate the F critical value, F alpha, we need three pieces of information: the numerator degrees of freedom, the denominator degrees of freedom, and the significance level. The rejection area is in the tail of the distribution. If F is greater than or equal to F alpha, or the p-value is less than or equal to alpha, then the null hypothesis is rejected, which implies that the entire model is significant. In our hidden cost case study, we will utilize the six-step hypothesis testing of the F-test. As we have three independent variables, the null hypothesis assumes the coefficients of all three variables to be zero. Next, we set the significance level at 0.05 in the second step. In the third step, we decide to conduct an F-test. For the fourth step, we consult a F distribution table to identify the critical value. We navigate horizontally to the section with 3 degrees of freedom in the numerator. Then we move downwards to 16 degrees of freedom in the denominator, locating a critical value of 3.24. In the fifth step, we observed the test statistical F-value is given as 21.9. This leads us to reject the null hypothesis and conclude that at least one of the regression coefficients significantly deviates from zero. Lastly, we conclude that the global test confirms that the outside temperature, the amount of insulation, and the age of the furnace all significantly influence the heating cost. We can employ the data in an ANOVA table to assess how well the equation aligns with our data. The SS column records the sums of squares for each source of variation. SSR denotes the regression sum of squares, while SSE represents the residual or error sum of squares. The mean squared regression, MSR, is calculated by dividing SSR by its degrees of freedom, 3, yielding a result of 57073. In a similar manner, the mean square error, MSE, is computed by dividing SSE by its degrees of freedom, 16, resulting in 2605. Since the F value is determined by dividing MSR by MSE, the final value is 21.9. Theoretically, this ANOVA table alone provides sufficient information to conduct the F-test. Notably, the p-value is a small number, closely approximating 0, and significantly below the designated significance level of 0.05. Consequently, we conclude that the null hypothesis is rejected. We now discuss the t-test. In the context of regression analysis, the t-test is used to assess the statistical significance of each coefficient in the model. In multiple regression, a t-test is conducted for each individual independent variable in the model. The null hypothesis for each test is that the coefficient for that variable is equal to 0, which implies that the variable does not have a significant effect on the dependent variable. The alternative hypothesis is that the coefficient is not equal to 0, which implies that the variable does not have a significant effect on the dependent variable. The t statistic for each independent variable is calculated by dividing the estimated coefficient b by its standard error. This ratio measures how many standard errors the coefficient is away from 0. If the coefficient is far from 0 in terms of standard errors, the t statistic will be large in magnitude, and the null hypothesis that the true coefficient is 0 will be rejected. The decision to reject or not reject the null hypothesis is based on the comparison of the calculated t statistic with the critical value from the t distribution, which depends on the chosen significance level, commonly 0.05, and the degrees of freedom. Alternatively, the decision can be based on the p-value associated with the calculated t statistic. If the p-value is less than the chosen significance level, the null hypothesis is rejected. In our hidden cost case study, we conduct a 6-step hypothesis test on the coefficient of each independent variable. In the first step, we state the null and alternate hypothesis. Specifically, the t-test statistics are calculated as follows. The t-value for the first independent variable outside temperature is -5.937. For the second variable, inches of insulation, the t-value is -3.119. Lastly, for the third variable, the age of the furnace, the t-value is 1.521. Based on a t-table, the critical value of t with a significance level of 0.05 and degrees of freedom of 17, which is calculated as 20 minus 3, can be found to be 2.12. Thus, we can reject the null hypothesis if t less than -2.12 or larger than 2.12. We can also compare the p-value with the significance level to conduct the t-test. In the test for both outside temperature and insulation thickness, we reject the null hypothesis. Outside temperature and insulation thickness are useful variables in explaining the variation in heating cost. However, the p-value of the third variable, age of furnace, is 0.148, which is higher than 0.05. So we may conclude that the analysis should focus on temperature and insulation as predictors of heating cost.